Hey, welcome! Today, we are going on a journey to uncover this secret world it's hidden in plain sight. It's all around you, it's inside you. We're talking about chemistry. But look, not in that stuffy, boring textbook way. We're going to see how it literally powers everything. Okay, let's dive in. Now, that might sound like a pretty bold claim, right? But I promise you, it's true. You have already performed dozens, maybe hundreds of chemical reactions today, and you probably didn't even realize it. I mean, think about it. From the second you woke up, chemistry has been running the show. Digesting your breakfast, that's just a big, complex series of chemical reactions. That coffee you brewed to get going, a perfect, delicious example of chemistry in action. Even the battery powering your phone, the plastic in your credit card, the gasoline in your car, it's all chemistry. It's not just stuck in some lab, it is the science of our actual daily lives. So to really get chemistry, it helps to look at where it came from. It's often called the central science for a good reason. It kind of bridges the gap between physics and biology, connecting everything from exploding stars to our own DNA. And its story, well, it stretches back thousands of years. It all started with some pretty wild ideas. You had early Greek philosophers who figured, hey, everything must be some combination of earth, air, fire, and water. Then, for centuries, you had the alchemists. These guys were obsessed with turning cheap metals, like lead, into solid gold. And look, while they never actually managed to do that, their endless experiments and note-taking accidentally laid the groundwork for modern chemistry, this rigorous, methodical science that's given us everything from life-saving medicines to the very screen you're looking at right now. So, how does a chemist really see the world? What's their secret? Well, it's all about learning to look at things through three different lenses all at the same time. Let's break down how this perspective really helps us understand matter on a much, much deeper level. Let's start with something you see every single day, a simple glass of water. To you and me, it's just water, right? But to a chemist, oh, it is a whole universe of fascinating interactions. So chemists break it down into three domains. First, there's the macroscopic. That's the stuff you can actually see and touch, like a giant iceberg or the glass of water in your hand. Then you have to zoom way in to the microscopic. This is the world you have to imagine, the one made of trillions of individual H2O molecules. And finally, there's the symbolic. That's the special language, the shorthand, like the formula H2O that they use to talk about it all. Okay, so first up, the macroscopic. This is basically the world you and I live in every day. It's the world we experience with our senses. It's the feeling of cold ice, the weight of a book, the color of a sunset. Anything we can see, touch, taste, or measure directly, that's the macroscopic domain. But here's the thing. To understand why any of that macroscopic stuff happens, you have to go deeper, into the microscopic domain. This is the hidden world, the one you can't see. It's where atoms and molecules are constantly moving, bumping, and reacting. It's where you find the real answers to questions like, why does water turn to ice? Or why does iron rust? And how do we talk about all this stuff, both the big and the incredibly small? That's where the symbolic domain comes in. Think of it as the essential shorthand of chemistry. These are the chemical symbols, the formulas, and the equations that let scientists everywhere communicate really complex ideas about both the visible and the invisible worlds without any confusion. So, with these three ways of seeing the world in mind, how do chemists actually discover new things? Well, they don't just guess. They have a time-tested recipe, a powerful process for asking questions and getting real answers. And you've probably heard of it. It's the scientific method. Everything kicks off with a hypothesis. Now, this isn't just some wild guess. It's an educated guess. It's a tentative, but most importantly, a testable explanation for something that you've observed. It's the official starting line for any real scientific investigation. And this is so important. Science isn't just a straight line from A to B. It's more like a cycle of discovery. It starts when you observe something interesting. That observation leads to a hypothesis, your testable idea. Then comes the fun part, the experiment, where you actually test that idea. And if the results keep holding up, experiment after experiment, that hypothesis can eventually grow into a scientific theory, which is basically the gold standard of scientific understanding. But you know what? None of this, the observations, the experiments, the theories, none of it works without a universal language. And in science, that language is measurement. It's what makes everything clear, precise, and totally unambiguous. Let me show you just how critical this is. Imagine this scene. A doctor prescribes a dose of 100 to control a patient's seizures. 100. What? Right? Is that grams? Milligrams? I mean, is it 100 grains of sand? The number by itself is totally useless. And in this situation, it's actually really, really dangerous. And this is where it all comes together. The units aren't just some tiny detail, they're everything. A 100 milligram dose could save that patient's life, but a 100-gram dose, that would be lethal. In science and in medicine, units can literally be the difference between life and death. So, to avoid that kind of catastrophic confusion, scientists all over the world got together and agreed on a standard set of units. It's called the SI system. This means that whether you're a scientist in Tokyo or Toronto, a kilogram is always a kilogram, and a second is always a second. It ensures that everyone is speaking the exact same scientific language. Okay, so we've got our units, but that's not the whole story. For a measurement to be really trustworthy, it needs to have two more qualities. It has to be accurate, and it has to be precise. And trust me, they are not the same thing. So, accuracy. That's all about hitting the correct target. It's how close your measurement is to the true accepted value. Precision, on the other hand, is about being consistent. It's about hitting the same spot again and again, even if that spot is totally wrong. This archery analogy is a perfect way to picture it. If all your arrows are clustered right in the center of the bullseye, you're both accurate and precise. That is the goal. Now, what if all your arrows are tightly clustered together, but way off in the corner of the target? Well, that's precise, but it's not accurate. And if your arrows are just scattered all over the place, yeah, that's neither. In science, we are always aiming for that bullseye. All right, time to play detective. Let's put everything we've talked about to the test. Imagine someone tries to sell you this small brick that they swear is pure gold. You're smart, so you measure it carefully. Its mass is exactly 90.7 grams, and it's a perfect cube, 2 centimeters on each side. So, the big question, is it the real deal? So how do we figure this out? With a simple but powerful tool, density. All we do is divide the mass of the brick by its volume. And when we do that, we get a density of 11.3 grams per cubic centimeter. Now, if you look at the chart, the density of real gold is way up at 19.3. But you know what 11.3 is a perfect match for? Lead. Our accurate and precise measurement just revealed the truth. It's a fake. And that right there is the power of chemistry in a nutshell. It gives you the tools, the ways of seeing, the method for asking questions, and the language of measurement to look right past the surface and understand what the world is really made of. So the next time you look around, ask yourself, what unseen chemical truths are hiding right here, in plain sight?